This is section 13.7, and this is Stokes' theorem. And we're almost done with our study of chapter 13. We have two more sections left, Stokes' theorem and divergence theorem. And these theorems are kind of just an add-on to what we've already done. So in other words, they are additional techniques to do what we've already been studying. The challenge of it is that these theorems are really complex and it just adds to the number of formulas that we already have in this chapter. So it's really, really, really important that you just keep all of these formulas in order and you know what they do and when they apply. Um, Basically, Stokes' theorem is a higher dimensional version of Green's theorem. And if you remember with Green's theorem, it relates a line integral to a double integral over a region. And it's kind of remarkable that this is the case. You know, we can take a single integral that's a line integral and we can evaluate it using a double integral. And remember with Green's theorem, you needed to have this closed region, and that was D. And so in this case, we're really dealing with the same thing. The issue is that with Green's theorem, it's really only good on a plane, and Stokes' theorem is basically Green's theorem but in space. So Stokes' theorem is just a broader version of Green's theorem. And at the end of this first page, I'm going to show you why that is, or at least hopefully I'll show you why that is. But Stokes' theorem, you can see down here in our formula, is it's a the line integral of a vector field equal to the double surface integral of a vector field, and we're using curl of the field, and then ds. And remember, s is a vector, and so that's going to be your surface itself. And this picture sort of denotes what we're doing. We're taking this path around this particular surface like this. You can see they drew in a little person here. But anyway, they're traveling around this surface, and this surface is not just on a plane, this surface is in space. And if it was on a plane, well, then we could just use Green's theorem. But since it's in space, we would utilize Stokes' theorem to sort of help us understand how to apply this. And again, we can use techniques from section 13.2, but sometimes, depending on the problem, it can be very difficult to use those techniques. And so that's why Stokes' theorem comes in and sometimes can simplify the process and allow us to evaluate a problem that's just too complex with the simpler techniques of section 13.2. You can read through the rest of our notes here. It just kind of goes through the development of Stokes' theorem. Obviously, the proof is very, very complex. There's also an alternative notational definition to it. I haven't seen that too often. Usually, what we're told is that we want to evaluate some sort of line integral, and if it is, again, if it's closed, so if it's not just a space curve that has a different ending point than starting point, we can't use Stokes' theorem or Green's theorem. But if it's closed and it's a surface in space, then it might make sense to use Stokes' theorem. I'm going to show you really quick the connection that Stokes' theorem has with Green's theorem. Let's just say that we had some sort of surface. So this is the z-axis and the y-axis and the x-axis. So let's say that we have some sort of surface in the xy plane. So pretend like this is, flat on the xy plane, and we didn't really care too much about the z-axis right now. We just had this flat surface. If that's the case, then any vector that we pull from here. So what I'm doing is I'm kind of talking about these vectors that we see in our diagram above. The normal vector n. Remember, it's a unit vector. That vector, no matter where we are on this particular surface, n would be equal to the components 0, 0, and 1, because it has to point upward, and in this case, because it's on the plane, it would have to point with the z-axis. So in other words, this is simply just the vector k. That's just 0, 0, 1. Okay, if that's the case, then if we're evaluating our line integral of vector field f of dr, that would be equal to the double surface integral of curl of f dotted with ds. And based on our formulas above, we have the surface integral of curl of f dotted with the vector n. And again, the reason for that conversion is that, prior to that, this s is a vector. We're making it an operator without a vector by taking the n vector out. We talked about that a little bit in section 13.6. But anyway, so we have that. And remember, if we have this flat surface on the xy plane, then what we have then instead of n is the vector k. So anyway, all of those things hold true. So this is what we're trying to evaluate, the line integral of the vector field. Because of Stokes' theorem, we can rewrite it like this. Because of our conversion from d vector s, we get vector n times ds. And in this particular case, n is a vector going straight up with a unit of length, and so we have just vector k. Okay, if we were to expand this and write this sort of in component form here, what we have is vector, curl f, which is going to be dr, dy minus dq, dz, dp, dz minus dr, dx, and dq, dx minus dp, dy. And that comes from the definition of curl, which we did in section 13.5. We're going to dot that with the vector k, which is 0, 0, 1. And in this case, what we're dealing with then, oh, and you know what, this, just go ahead and change this part right here. This should be dA and dA. Okay, so anyway, so if we notice what this simplifies to, we get the double integral s, and if we were to multiply these components, so we have our first component times 0, second component times 0, third component times 0, guess what we get? We get dq dx minus dp dy. That is Green's theorem. And so this just, I guess, shows kind of in a very simplistic case that Green's theorem is just a special case of Stokes, or in other words, Stokes' theorem is sort of the overarching theorem, and Green's theorem sits underneath it if certain conditions apply. Okay, we'll continue with our examples on the next video.